In Unit 9, I'm going to discuss the forces associated with objects on slanted surfaces or inclines. And in section 9.1, we're going to focus on the components of gravity relative to an inclined plane. It's very common to use a coordinate system that's aligned with the direction of gravity. We pick the y direction to be the direction of gravity, and then the x direction is perpendicular to that. And that's really good for problems where we have an object moving horizontally, moving vertically, or if we have a projectile. But in other situations, this coordinate system is not all that useful. It makes the math very, very difficult. So we try to pick a coordinate system that is the most convenient. And when we have an object that's on a slanted surface or an inclined plane, then it's useful to align our coordinate system up with the incline. So this is what our coordinate system is going to look like. We're going to line the x direction parallel with the incline, and the y direction is going to be perpendicular to the incline. In these types of problems, motion is only going to occur in the x direction, because if it lost contact with the surface, then it wouldn't be on an inclined plane, and this wouldn't be a useful coordinate system. So the object is always going to be in contact with the incline for this type of problem, and it's not going to move in the y direction. It won't move into the plane or away from the plane, and so therefore the forces in the y direction are always going to be balanced. So on the next few slides, I'm going to work out some shortcuts for the weight components for an object on an incline. We're going to have to find the components of the force of gravity or weight, because now weight is going to be acting at an angle to our coordinate system. Before, we didn't have to do this because the weight acted along the y direction. And in order to work out these components, first we're going to need the angle that weight is the weight force is going to make with the coordinate system. And here's a little diagram that's going to be helpful. The problems that we have involving an inclined plane are going to give you what's known as the ramp angle, and we're going to call the ramp angle theta. The angle that we're looking for is this angle, theta prime, and theta prime ends up being equivalent to theta. You can see that in these few diagrams. Here we have a right triangle with these two blue lines. And so theta plus this other angle phi that we don't really care about have to be complementary and add up to 90 degrees. Well, we're trying to find theta prime, where theta prime is the angle that is made with the direction of gravity, which will be this line right here, and normal to the surface, right? So we have this other right angle here where theta prime and this other angle that we don't care about, phi, also have to be complementary. Well, if they're both equal to 90 degrees, theta plus phi has to equal theta prime plus phi. Well, we don't care about phi, but it's going to cancel out. If you subtract it from both sides, then we're left with the fact that theta and theta prime are the same thing. And we're going to use that on the next slide to find the components of the weight force. All right, on this slide, I'm going to work out some shortcuts for the weight components for an object on an incline. Here we have our object on the incline. We're given the ramp angle theta. The weight force is acting down, straight down. Gravity still acts in the downward direction. And we're going to separate that weight into the components. One of the components that I have drawn in purple and labeled WD will stand for the weight that acts downhill, the downhill component. It will always act downhill. Don't draw the component of gravity acting uphill. Gravity tries to drag things downhill. The green arrow is going to represent the component that is acting into the incline, perpendicular or normal to the incline. So Wn stands for the normal component of the weight force. And as noted on the last slide, the angle between the weight and the normal to the surface direction, which we're going to call our y direction, is going to be the same as the ramp angle theta. Here is the weight force and its components, just redrawn so that I can translate it into a right triangle. Okay, the downhill and the normal components are perpendicular to each other by definition, and the angle theta is the angle between the normal component and the weight. And so now we can use our trig functions to work out some formulas for the downhill and normal components for weight. The sine of theta is going to equal the downhill component over the weight. The downhill component is opposite the angle theta, and the weight is going to be the hypotenuse. So sine relates the opposite and hypotenuse of a right triangle. If we rearrange this for WD, which is what we were looking for, we get weight times sine theta. We can do a similar thing to work out the normal component. The normal component is adjacent to theta. Weight is the hypotenuse, and so cosine is the trig function that relates the adjacent side to an angle and the hypotenuse. So we can rearrange that for the weight force normal, and we get weight times cosine of theta. Now, here's some patterns that you should be paying attention to. Here are the graphs of sine and cosine for angles between 0 and 90. We don't care about any angles bigger than 90 because then you'd be beneath a slanted surface, and we're really never going to have that type of situation. The downhill component is equal to weight times sine theta, and you should notice from this graph that sine theta increases as the angle increases. Sine theta approaches 1, and so the downhill component of the weight is going to increase as theta approaches 90. It will reach a maximum at 90 degrees, but you should note that an angle of 90 degrees would be this situation. It would be an object on a vertical wall, and so the downhill component would just be the weight. So what about the normal component for the weight? Well, the normal component for the weight depends on cosine theta, and as you can see that cosine decreases as theta is approaching 90. Again, that should make sense if we remember that 90 degrees is this situation here, a vertical wall. The vertical wall does not have to exert any outward normal force to keep the block from moving into the wall. It'll just not do that on its own.